Hi, good evening and welcome to the ZP Developer Zone. So we like to do this Developer Zone every week. Meant to go live on the 22nd, but it's the 21st tonight. For me, it's a Saturday evening. Feels like a good time to do this. So let me just jump into it. I'll just jump straight to the questions. So as I say, it says the 22nd of September 2024. Don't worry, it is actually the 21st if you're watching this live. With that said, if you're looking to buy anything off the web store at the moment, we do have this 10% discount code, and you can find the web store here. If I'm talking fast, it's just because it is a Saturday night, and we've got something like 6 questions to get through. And I mean, I do have a bit of technology in front of me as well. I do have some questions about lead and nitrate, and I realise I need to put a sensor on that shortly, so I'll just reach out and grab some sensors. And I have a flow cell in front of me as well, and all that will become kind of slightly apparent in a short while. As I say, if any of the technologies or you find yourself onto our web store, then that code will work in December. Let me go forward a little bit quicker now and just sort of touch upon the questions. So somebody's interested in, I'm not sure they're so much interested in the lead sensor, I think they're just curious. And on this web store, we don't mind answering curiosity questions, and they want to know how we differentiate lead. So I can make a lead measurement using my smartphone and using the sensorAfter platform. sensorAfter's platform is very powerful. If anyone wants to do like a point of need diagnostic, things like lactate, glucose, creatinine, etc. This is a very powerful little platform that can take our sensors and using the hardware, using the app, and using a cloud computing system that we have called Julie. I'll just quickly share what Julie looks like. Julie is this system here where every time I do a test on our technology, the data actually goes up into the cloud. Anyway, back to the question. So somebody was interested in how we get specificity on the lead, and I will jump into that shortly. Somebody else was asking about the generation 2 glucose sensor and lactate sensor. What's the effective measurement range? Look, we build all of our sensors to be effective in the clinical range. I say that very carefully because it's kind of like a filter. You know, if you're not quite sure what the clinical range is, then possibly, you do need to find that out, because if you do know what the clinical range is, then you will definitely find out that our sensors are always designed. I'm going to be a little bit careful with that because somebody will, but we, typically at ZP, our sensors can be used in many applications. And just to sort of show you the diversity of things here, this is just a spontaneous thing. I've just reached out and just grabbed some coffee here. So this is some coffee suspended here. So we're actually detecting caffeine. Here's some chili sauce in a solution here. So we're detecting capsaicin. But lots of what we do, and we are ISO 13485. So ZP carries one of the highest quality certifications in the world. It's ISO 13485. It's for the contract development, contract manufacturing of electrochemical biosensors. And anyway, so you're asking what the effective ranges are. For both those sensors, it will always be the clinical range. What's the accuracy and repeatability of the sensor? And this is a really important question. The sensors that ZP will put on its web store are for allowing you to achieve a TRL3. Just last week, we were doing human studies using our biosensors, and this week, we've been doing animal studies using our biosensors. But I need people to be well funded to really be able to kind of engage with us to start digging into the accuracy and repeatability of the sensors. Because the quick answer is our sensors are only part of the technology stack. So later on, I'll see a question where they're going to take a sensor, put it in a flow cell, do some calibration, do some rinsing. See, when you have a system like that, you can then have a very repeatable measurement. But it's very important to understand that the accuracy of a medical diagnostic is 90%. Well, the sensor is really important, but actually it's the entire system. So I would actually ask you, what's the accuracy of your system? And the answer possibly is, I haven't built it yet. Okay, if you haven't built it yet, have a budget, engage with ZP, and start developing these things. Let's say, is a buffer system required for operation? Absolutely not. You will see some sensors in a bit where it's impossible. I think it's question number 6. Impossible to put buffers onto these sensors. Can we work in bodily fluids or blood? So let's be very clear. Our generation 2 lactate sensors were in an animal study this week in the jugular, in the blood flow stream? So the quick answer is yes. I will not provide additional information because we do need people to be, funded enough to really engage in these conversations. These are not light conversations. If somebody's really trying to develop a medical diagnostic, a medical device, it's really important, to kind of have that gravitas, that amount of funding that you can, truly do it. Otherwise, it's just dangerous to answer these kind of questions. Question number 3 is much easier. This is about EIS, electrochemical impedance spectroscopy. Now I understand their question a bit more. That they're building up what's called a self-assembled monolayer, and they're just really wondering, like, if a potentiostat, and I have a potentiostat here, if potentiostats are so good, why do I have what's called an IR drop? Then I don't think they've got a problem. They're just wondering why it doesn't compensate for something called an IR drop. The point is, with many biosensors, this is obviously a biosensor here, and I might actually go to this one here. The reference electrode is pretty close. You see that? You see I've got a black line in the middle. That's the working electrode. The reference electrode is this kind of silver line wrapped around the edges, and then there's a sort of rectangular electrode there as well. It's not the one that's wrapped around, but there's a rectangular. That's the counter electrode. You can see how close we've actually got the the reference electrode to the working electrode, and we've done a really good job actually, because the way it wraps around that working electrode, we really are sensing the potential between the counter and working. But you can see that there's still a millimeter gap, and that's that millimeter gap where we're going to get the IR drop. We don't suffer, by the way. I got a suspicion these people might be actually using a kind of a more larger electrochemical assembly rather than using screen-printed electrodes. If they've got problems with screen-printed electrodes and IR drop, then I strongly suspect they're not using our screen-printed electrodes. But that said, I will give them some detailed answers to that question now, or shortly rather. Question number 4, somebody's interested in our nitrate sensor. They want to use it with their electronics. I just want to say that ZP has built a really good technology stack where we can take a nitrate sample, put it on one of our sensors, put the sensor into the electronics, make a reading. I'll just scan the QR code for nitrate actually. Make a reading, and what am I going to say? And that reading will go to the cloud. But when it goes to the cloud, I just want to be very clear, we have an API built into this. So if you are a developer and you are interested in getting the data, the way ZP has built this technology stack, you can skip the whole, I built my own datalogger. You don't need to have done that now. You can actually just skip straight ahead and actually kind of, obviously engage with our electronics, engage with our sensors, use the API, let's say, and actually you can get hold of the data. But I just want to be really clear that we don't support the nitrate sensor without our electronics, but there is an API, so you can actually get hold of the data. Question number 5. This is an interesting one. So they want biosensors, and they can use them in a flow cell. They'll probably do gamma sterilization. They're interested in a couple of our sensors. Can they be used intermittently? They can. See, this person's having a very robust setup. And what I mean by that is they put a sample in, they get results, they do a wash, they do a calibration, they put a sample in, they get a result, they do a wash, they do a calibration. That's a very, it's really going back to question number 2. See, what's the effective measure? What's the repeatability and accuracy? It really depends on how you run that sensor. And in this particular case, when somebody's making more like a clinical analyzer or bench side instrument where they can actually afford that kind of workflow, you can understand you can actually get really good, let's say, accuracy, because you have a flow cell, and I should sort of go, they may have a flow cell. I have one here actually. They may have a flow cell similar to one like this. In fact, I suspect this is more medical grades, and this is more kind of R&D tool that we use when we're engaging on client programs. But we can slip a sensor in here, and then I've got a flow cell assembly that we can effectively put on top of it. But they want to measure things like glucose, lactate, oxygen, pH, creatinine, and electrolytes. And in fact, I think we've got some really good sensors around that, especially for the application. But of course, ZP, we'll sell biosensors on our website, but we'll only sell them so people can do a kind of proof of principle, a technology readiness level number 3 kind of proof of principle. If people really want to use them in a medical diagnostic, the ZP business model is quite different. We really get involved in client projects. So we're in part, we make sensors, electrodes, we sell them to the R&D market. We make potentiostats, we sell them to the R&D market. We may even make flow cells and sell them to the R&D market. But people who are serious about getting into medical device, medical diagnostic, we are ISO 13485. At that point, our ISO system is going to kick in place. But unfortunately, the first barrier, let's say, to working with ZP is whether you have sufficient budget. And so we do only work with clients with budget, but even though we carry let's say, some of these sensors, we will only engage with people on medical technologies unless they've got the right budget in place. But I'll come back to that anyway. Is sterilization feasible? I mean, at ZP, I think we've been involved with e-beam sterilization, ETO, ethylene oxide sterilization, gamma sterilization. So sterilization is definitely feasible. I think at the moment, in fact, I think the thing that we've done most of is actually e-beam and gamma, but we're actually about to put some enzyme sensors through ETO, ethylene oxide sterilization as well. And then lastly, this might be anyone, if you see your questions here, wait till the end anyway, because you're going to see some, I don't say crazy, but you'll see some interesting sensors on people scenario as well. So somebody's wondering about the specificity of our lead sensor. So our lead sensor is pretty cool. We've got a technology stack. That means that if I scan QR codes, I can program this device. That in fact now I'm on caffeine. That's one that we've just launched. I'm really quite excited about that. Or we can scan another QR code and go to total antioxidative status, or scan another QR code and just trying to get the lead one actually. I've got too many of these close to one another, so I need to change my angle slightly. There we go, I've got lead now. So we do have the capability of testing lead. It's a really neat little device. In fact, I was showing it to some environmental chemists the other day, and they were like, I didn't even know this kind of technology was possible, kind of response. But that was pretty cool. So we do have a technology for measuring lead, and actually it works in a kind of way that, in fact, we can make a measurement, we can send that result to the cloud. In fact, there you go. We were using those sensors on our lead system. We talk through, how to do it. In fact, I've got one of my engineers, we've got a video online where we actually do this kind of demonstration. You can just see them adding the sample here now. There it goes. The beautiful thing about electrochemistry often is, our sensors really only require a drop. Theoretically, a electrochemical biosensor only requires about 300 nanoliters. In that particular case, we're putting 50 microliters down, because then it covers the 3 electrodes. But if we made the investment and built a microfluidic system, then we could reduce that down to like 300 nanoliters. And then the nice thing about this is that when the assay comes to an end, it actually uploads the data, processes the data, and gives back a result on the phone, so that somebody can get the kind of ppm of lead actually on their phone. I think this one came at about 362, so it's quite high. But then all the data actually gets saved to the cloud as well. So you've got a really strong signal in this particular case. I mean, it's it's a synthetic sample. But I wanted to say is it is a neat system. We can do many things like nitrate, lead, caffeine, capsaicin, glucose, lactate in this form factor. It's all QR code driven. It's a smartphone, it's an app rather, you can put in your smartphone. It drives it. It sends the data to a cloud system called Julie, which is proprietary to ZP, where we can process data and we can send the results back to the smartphone. It's very, very powerful for going from 0 to MVP, and I'm going to use the word MVP, or the acronym MVP, and I'll call it minimally viable prototype in this case. Got to be careful when you say product, because then people think, oh, a medical product. It's like, no, you got to be careful. That's got to still be, FDA approved, etc. But how do we get the specificity? We're using a technique called anodic stripping voltammetry. Just out of interest, if you stop the video, you can actually download these apps on your phone and actually get a sense of the cloud connectivity that we actually have on this. But lead has a very distinctive position where when we're doing this kind of work, we can see zinc, cadmium, lead, arsenic, copper. At the moment, we've only unlocked lead, but it's easy to get the specificity because lead has its own stripping or anodic stripping voltammogram. And so we can see from the position that it's lead, and we can see from the area under the curve how much lead is in there. And copper, for example, if that's is somewhat removed from it, and we have a very, very, very good data processing system called Julie. Anyone who's using our technology stack, when I say our technology stack, this is the SensorsAfter from Zimmer and Peacock. Anyone who's using this is then got access to Julie, and it's a very powerful way of processing data. So if you are looking to do heavy metal detection, just know that the SensorsAfter technology stack does have a lead assay built into it. Our business model at ZP is actually to, through paid programs, is to help clients and academics bring their technology to market. Question number 2 is really about lactate sensors. And they were kind of worried whether these would work in like real samples. Just out of interest, this is a whole bunch of lactate sensors that have just not come in. They were off for an animal study in the USA, where these lactate sensors were being put into animals in different various parts of the animal to determine the lactate distribution around the animal. This is serious work when you're doing this. I mean, it's not low cost to do that kind of work. Please stay to question number 6, because you're going to see that another variation on this. But I think their questions were around the lactate 2 and 1. They were saying that they couldn't find enough information for their application. If you've got enough budget, then you probably need to engage ZP so that ZP can help you with your application. The effective range is always the clinical range. The accuracy and repeatability really depends on the application itself. So, for example, if it's in a flow cell, that's one thing. If it's a point of care diagnostic, that's another thing. If you're measuring interstitial fluid, that's another thing. No, you don't always require buffers. Depending on the application, you might end up using buffers. Can it be used in whole blood? Well, those generation 2 lactate sensors were definitely used in whole blood this week. And if you can't find information on the website, then probably if you have the budget and you can engage with ZP in a sort of deep, meaningful way, then more information can be provided there. Question number 3 is really more of a sort of deeper dive into just fundamentals. So ZP, we manufacture all sorts of electrodes to help people in their assay development. And I don't think these particular people are actually using our gold electrodes, but I think they're building up a self-assembled monolayer where you basically put thiols onto a gold surface. It's really kind of robust science, and they're probably then using what I call a redox reporter to see the formation or the successful formation of that self-assembled monolayer. Now you can use EIS actually to, so if you measure a pure gold surface, I've drawn this by hand, so sorry for a slightly wiggly line, but this is what we call a Nyquist plot, and I'm looking at an impedance spectrum. Well, I'm looking at a Nyquist plot from an impedance spectroscopy experiment, and then when you form the SAM layer, you should actually increase what's called the RCT, the charge transfer resistance. Now the solution resistance, if you're setting everything up correctly, should actually stay the same. What this person is saying to us is, why am I getting solution resistance if I'm using a potentiostat? So I do understand the question. And the answer is, and I know that I've used this slide before to try and answer this question for this person, but I'm going to dig in a little bit deeper here and say, look, here's a working electrode, here's a reference electrode, and in fact, what's going on here is I might actually just use this for a second. Laser pointer, working electrode, reference electrode, counter electrode. All right, so I'm just going to escape from that and just say working electrode, counter electrode, and we're pretending that we can model the way the system behaves between the working and counter electrodes using this Randall circuit. And then between the working encounter, we have this reference electrode, and you can see it in my little image here. There's the reference electrode, there's the counter electrode, there's the working electrode. So it's, we're very good at actually the way we've placed that reference electrode, because actually we have placed it, next to those two electrodes, so we are sensing the potential. They're not worried as such, but what they're saying is they're interested in the charge transfer resistance. But why, if they're using a potentiostat, should they have this resistance here, which actually leads to something that's called an IR drop. So when I say IR drop, there's a current flow between the working encounter, and they're sensing the potential here. But some of the potential that they're essentially sensing, because what they're trying to do is they're trying to control the working electrode potential by controlling its potential versus this reference electrode. But some of the potential is lost across here, and this is the solution resistance. And why is this happening? Because the electronics doesn't know anything about this gap, but there's a minute gap here of a few millimeters, and that could be the source of your resistance. It's because you can't physically put the reference electrode right next to the working electrode. You can put it close and a bit closer and a bit closer, but you can't get it absolutely there. And so in the end, the potentiostat is pretty good at compensating for potential losses, but there's a physical limitation. It's how close you can place it next to the working electrode. And you can appreciate there's only so close you can get, and there's still a little slug of solution. I really have a strong suspicion that in your experiments, you probably don't have that much of an IR drop. If you do, I would say send me the data, because I think, I could probably look at it and say there's something wrong here. Send me your data, and then I will have a look at it. So let me just go forward a little bit. Now you can reduce the IR drop the closer you can get that reference. The closer you can get that reference, the less IR drop. But most people are using these kind of screen printed electrodes. I really don't think I see much of a problem with IR drop. And once this person says I'm using SAM layers, etc., then I know that they're really doing a true kind of immunoassay type electrode. They're in aqueous solutions. They really shouldn't be having an IR drop problem. If they have, there's something else. I think they've got some problems, and probably best. The good thing about this, what we do on this particular video channel, is if people send us data, we analyze it, we comment upon it. So and many of these people who are asking questions are not ZP customers, but we do believe in helping the next generation of entrepreneurs or next generation of PhDs, etc., to get their science done, get those PhDs done, get those businesses started, get that funding sourced, etc. Now, number 4, somebody wants to use their own electronics in a nitrate sensor, and I just want to say that ZP, we try to reduce all the gaps that are stopping people from making an impact, and an impact in agriculture is important. So that means we've developed the sensor, we've developed the electronics. You can put a tiny drop of the sample on there. You can use a QR code to unlock things like the Nitrate app. In fact, I might do that when I think about it. And you can analyze that sample. You can get the data to the cloud. The cloud will process that data. I'll just diminish this for a second. And actually you can get nitrate data back on your phone, for example. And as I said earlier on, the kicker as well is all our data goes to the cloud. It's behind your username and password. I can't see it. But just know that actually you can make API calls upon this database. So I really think that the smartest biosensor developers of the future will be more like app development than actually necessarily having to do all of the steps. I think you will always need to make your own sensor. Electronics is becoming very commoditized. Even the apps are becoming very commoditized. You can find our app for free on the Google Play Store and the Android App Store. And actually our database allows you to make an API call upon the data as well. So we're really trying to reduce barriers. And so when people want to develop electronics for themselves, I applaud it. And it's good from a teaching perspective. But adding value in the world of biosensors, I think it's become a very commoditized technology these days. And actually you can get suitable electronics in all sorts of, let's say, places. So the quick answer is we don't sell the nitrate sensor unless it's with our electronics. I've slightly mislabeled this one, but this one is actually about, so somebody, I've been following this company for quite a few years now, is making sounds like a sort of bedside or maybe clinical analyzer type technology where there's a lot of flow cells involved, where they have a kind of, they flush, they read, or rather they read, they flush, and then they calibrate. So it's a very forgiving technology on sensors. So this will allow them to have, good accuracy. At ZP, we do have a bunch of sensors, and people are welcome to buy them and use them in their kind of proof of principles, but we don't expect people to buy them and use them in clinical trials. If that's going to be the case, then we really need to be heavily engaged. There needs to be a budget available for ZP so that we can ensure the proper use of our sensors, but they can be used in this kind of modified fashion. Is sterilization feasible? It is feasible. We both know that sterilization, really, the sensor is going to be probably in a cartridge and then sterilized as a package. So I cannot make blanket statements about sterilization because it's probably, when we've been involved in sterilization projects, in fact, I'll just grab a sensor now. You grab a sensor like this, you'll put it into some sort of flow cartridge, that'll be packaged, that'll be boxed, those boxes will be put on pallets, and the whole pallet is sterilized. That's the kind of thing we've been involved with. So I can't make blanket statements because until it's been through that process in your particular device, I just don't know is the quick answer. But modular flow cells is completely fine, and gamma sterilization I think is fine as well. This is just a last one. I just want people to realize that at Zimmer and Peacock, okay, let me just back up a bit and take it a bit more slowly. Okay, we're pretty good at doing R&D systems, so people can come in, if they're running amperometry experiments, perfectly fine. If they're measuring open circuit potentiometry because they're doing electrolytes, perfectly fine. If they're actually doing EIS, which some of the inquirers tonight are doing EIS, that's perfectly fine. If you're building SAM layers, you might want to do cyclovoltammetry, that's square wave. So we're familiar with all this kind of deep science, but the science gets pretty serious at some stages, and this is science getting pretty serious. So at ZP, we're very good at wearables. It's a busy market these days in the world of biosensors. There's lots of people saying they can do it. Maybe there's less that actually can, but we're really good at actual putting sensors in, through, on top of, underneath the skin. And I do talk about it, but this is literally what's going on here. One of our biosensors, somebody's asking a question earlier on, can it be used in things like blood? Yeah, our sensors can be used in bodily fluids, and this is an example of us doing this, in fact, just this week, putting a sensor in place. So this is something that we do. As I say, just this week we did pig studies, and if I mentioned we'd said that we did this week, I meant to say we actually did it last week. And here you can see the willing volunteer essentially being mounted up and all the sensors applied in this particular case. But I think you get a sense of how serious we are. This is not some academic program or nice to do. This is quite serious stuff, and we will step up ourselves and be involved in those particular programs. And here I'm actually having my blood tested to help understand the sensor itself. So I do want people, if people are wanting to develop medical or wearable or well-being sensors, ZP will step up and get involved in this work. But unfortunately, the thing that's holding people back is not always the science or your questions. It's really, have you raised the funding? Because I think this image alone would show you what's going on here. You've got two masters, two people with masters, two PhDs, all focused essentially on one experiment. And this is a kind of, this kind of work is not low cost, not when it's done professionally. And so, but we are happy to help people in their medical diagnostics as long as the budget's in place. How can we be specific towards lead? Well, lead actually has its own specific stripping peak. Our generation 2 lactate sensors and glucose sensors are used in medical applications. I've given you some strong hints tonight about that. The effective range is always clinical. Accuracy and repeatability is all about the application itself. Tonight we've talked about flow cells, we've talked about point of care diagnostics, we've talked about wearable sensors. So you understand that we're dealing with all these different types of applications. Buffer is not always required, can be used, but it's not always required. We are putting our sensors into real bodily fluids. With your IR drop question, we do put the reference electrode in a really good place next to the working electrode, but there's a millimeter gap there, and it's that millimeter gap. The potentiostat doesn't know whether that gap even exists. So the potentiostat is ignorant to it, so it's controlling. But if there is an IR drop between essentially the working and reference, I don't have a big problem with it because we're using screen printed electrodes a lot. Our electrode setup is really repeatable, and because you are doing EIS, you should know it. If that solution resistance is jumping all over the place, you've got an electrochemical cell setup problem. Send me the data. I'm pretty good at it, analyzing data. And I would also say that it's a good period for the next 2 weeks. Things might be a little bit quieter, so if anyone has any troublesome data, send it in to me. With the nitrate sensor, we're not supporting third-party electronics. With the startup, I think this is an exciting application. I think it's a very doable application, but it does require really a correct level of funding. I mean, what with ZP, we kind of like, if somebody comes to us with an idea, we like them to be on the market within 2 years, and we've definitely done that. But it does require, a rapid sprint and on the market. So if somebody's come to us, we've developed, we've manufactured, we've got CE marking, and they're on the market. But, when things are stretched over years, it's a shame. Get the funding, get it done, get it on the market. That's where, it's just sort of the way we like to get it done. And also, if people are interested in wearables, we're super serious about wearables. We've been doing some animal studies this week, and last week we were doing, let's say, animal studies, but on Homo sapiens. And if you have any questions of ZP, please don't hesitate to reach out to us. Okay, thanks very much.